for being here early, and thanks for inviting us again to speak here. It was a fantastic event in Mountain View, so glad to be here and talking. So let me talk to you about the robotic character platform that we are building, that basically is behind the robotic characters that you might have seen by now. Okay, clicker isn't part yet. Thank you. So it's also a way to go from screen to reality, and we have an interpretation of physical AI for entertainment robotics that I want to share something about. Okay, so robotic characters. What are robotic characters? I think the VDX droids that are created are a good example for what a robotic character is. So they're freely roaming in our parks. What's interesting about them is they can freely interact with objects, as you can see here. But you as a guest, that's how we call human beings in our parks. You are our guests if you are coming to the park. You can actually co-direct the story. You can interact with them in new and meaningful ways, and every time you come back to a theme park, one of our parks, you have another story being told. So you can influence that story as a guest. So I think they're a new way of augmenting our lens and really fun to interact with. So what's interesting about them is that the inspiration actually started on the screen in the game. So what served as an inspiration for our VDX droids is the VD1. So technically it started on the screen, at least the inspiration. And so that if you think about the VD1 as being the puppy, we then built the VDX droid, that's sort of the adult version of a VD type droid. What's unique about them is that they appear first in a park. So a new character that we built appeared in the park first, and is now being part, or you can see it in the Mandalorian and Grogu movie. So the movie is in the theaters. I encourage you to go see it. So, you know, inspiration started on the screen. We then brought the character to the park first, a new character, and then it appeared on the screen. So then we started to work on Olaf after the VDX droids. So here is Olaf walking around at Disneyland in Paris last November. And so this is a quite challenging robot to build. So what the ambition was to truly bring an animated character to life in the physical world. So here is the robot again, some interactions with the robot in our lab environment. So I think it's just enormous fun to interact with this character. So what's unique again about this character is that it started in a movie, and not just a movie, it started in an animation movie. And each character can do a lot of things that it can't do in the physical world. So if you look at Olaf, no one who builds a functional robot would ever build such a robot with such a gigantic head. It's just proportions that are extremely hard to bring alive in the physical world. So let me talk about how we designed and built new robotic characters within months. So that's the ambition. We want to build new characters, bring them alive in the physical world within months. So the VDX droids took us less than a year from concept to 3 fully finished droids that we brought to the park for a day. And Olaf took us about 4 months, with lead time 6 months. So we really tried to develop quickly. So one key ingredient is that we use modular hardware components. So we rely on an actuator family. So you have a few actuators in our library that we reuse across characters. Very important, you need to understand your actuators in your software stack, runtime system, but also most importantly, in your simulations. We also have a family of sensors because we want to make these robots more autonomous in the future, and we have a few electrical boards, custom boards. We have a battery module that can remove and recharge. We have also real-time compute on board, Jacksons. Those are important for autonomy solutions. The GPU is very important there. We have custom boards that facilitate the communication between actuators and sensors and the real-time computer. So we reuse those across the characters. That's how we scale, because we understand them well in software. So we have some additional hardware that we use. We call them show functions. This is usually character specific. So modules are character agnostic, while we have show functions that are character specific. For example, a drone needs antennas that you can actuate, needs eyes, so you use LED arrays, headlamp for scanning, important for an explorer voyage. So things like that, we usually custom build per character. But for Olaf, we actually used exactly the same family. With one exception, we had to add an actuator to our actuator family. But again, the speed comes from reusing hardware modules. Because then you know them very well in your runtime system. And runtime systems are hard to build and get right. So if you use the same components, you can actually reuse the runtime from a previous character when you build a new character. The other key ingredient is reinforcement learning. So we no longer program these robots to walk and so on. They learn to walk in simulation. You see this process here. So you have artist-specified motion, and in this simulation environment, the robot learns to walk. So you have a so-called control policy that is being trained. That's a simple neural network. So at the beginning, you initialize it with random weights, this neural network, and the robot falls over all the time. But over time, it actually learns to imitate this artist-provided motion while always keeping dynamic balance. Remarkable how well that works. And so we do that at scale. We do that with, for this particular example, 4,096 simulations at the same time on a desktop GPU, right? So this scales incredibly well. What amounts to a decade of training in the real world, you can actually do on a single desktop machine within hours or a couple of days. So we push the robots quite a bit with forces and torques. You see these arrows in blue and green. So it applies those to the pelvis and the 2 feet so that the robot learns to be robust. We also vary the terrain. So these robots at this moment in time, they were actually blind. So then they learn to be really robust. So you see this here in action. So if you think about you yourself walking over such obstacles completely blindly, you might fall. And it's just amazing what reinforcement learning can do for you. So again, we don't program these robots any longer, they learn to walk. And then it's a zero-shot deployment onto the robot. So we applied the same technology to our Olaf robot. So they learn to walk in simulation. And so here we see a reference animation and what we can achieve on hardware. And you see pretty much a perfect match. So if you run animations directly on a robot, that would not work. The robot would actually fall over. So because you have a simulation that accounts for gravity, and you also have these mechanisms to make these policies robust, the robot can actually balance even if it would accidentally run into something. So again, amazing technology. But for Olaf, we had to innovate a bit more. So for example, when you try the first policy on hardware with just the 2 legs, we heard Olaf walk. You should never hear a snowman walk. And so we had to figure out how to reduce the impact noises. So we started introducing new rewards that reduce impact. And so these rewards basically just ask that the forces that are applied from the environment onto the robot, that they are minimized, okay? And so that has a positive effect, because if you reduce the forces, then you usually hear the steps less. So I show you a video with a before and after. So this was before. So it doesn't sound like a snowman. And here's after, when we introduce this impact reduction methods. And so I think that's actually quite a remarkable result, because think about it, if you had a humanoid robot, you can reduce the impact forces, you can actually increase significantly the longevity of a robot. Because, for example, the actuators don't wear off as quickly. So this is a really useful reward to use for robotics in general, and Olaf served that as a platform for us to innovate on that front. So our mission is basically to make robots as believable as possible. You should never see the mechanical system or never hear a mechanical system. You should see and hear the character. The character is at the center of it. All right, so the second innovation that we had to introduce for Olaf was we had to deal with overheating. So I talked about this gigantic head of Olaf. if you just build a functional robot, you would never build a robot with such a large head, because the center of mass moves up in the body. So that those, the large head and also the thin neck was a challenge, because we had to fit 3 actuators in the thin neck. Right? So we didn't have a whole lot of space for actuators, so we had to use small actuators there. And so when we first tried policies, we saw that if you lean back with the head, the actuators started to overheat over time. So we introduced thermodynamic modeling for the actuators. So we truly simulate not just the mechanical system, but the heat development in our actuators. So Olaf, with those rewards, learned to manage its own heat and frankly not melt. So as you know, Olaf loves summer, so he should be able to walk around when it's hot outside. So you see these side-by-side comparisons here. So thermal rewards, you can actually make sure that you never exceed a certain temperature threshold. And again, the robot learned in simulation to do that. So if you add to your simulation, you can get a lot more out of this learning-based control. So you see that you have a test motion, right? At some point in time, if the temperature rises too much, the Olaf robot is just a head, moves forward, and then it will return to what an operator wants to do. So it's really subtle. The changes are really subtle. You would never perceive that as a human being. The operator might perceive slight variations from what you want to do with a two-joystick controller, but this truly prevents overheating from happening. So that's again useful for humanoid robotics in general, because if you have humanoids, for example, work on a construction site outside, right, and it's a sunny summer day, you want to make sure that your system can prevent failure due to overheating. So again, Olaf served as a platform for us to innovate, I think, robotics in general. So I want to briefly talk about the seam to real gap. That's actually a question that we are asked quite a bit. What are the tricks to reduce that seam to real gap? How can you learn in simulation and zero shot transfer onto the robot? And the robot doesn't learn anything in the robot anymore, right? It's zero shot transfer. You just upload these neural networks after training and the robot just starts to walk. So how do we achieve these really polished motions on the robot? So one item is that you have to understand your simulations quite well. So sometimes it's actually truly worth refining your simulators. So when we started working on these 3D walking robots, we looked at the actuators first. We characterized them, we rotated them, we built basically a characterization device. So we fully understood the mechanics of an actuator. And so what's also important is QDD actuators usually have backlash. And so each actuator has about 1 degree of backlash. So if you have 5 degrees of freedom legs, then you have 10 degrees of freedom, or 10 degrees of backlash between the legs. This is significant if you think about this. This is just play, right, in each actuator that accumulates. So we account for backlash in simulation, and by doing so, you can get this very polished motion. So we extended the simulators where necessary to close this into real gap. So sometimes it's really worth working on your simulator. But you have to meet sort of the accuracy versus speed trade-off. You need speed for reinforcement learning. So these simulations run much faster than real time, and you parallelize many of these simulations at the same time. So you have to find the trade-off, but accuracy still matters at times. But the rest you do with so-called randomized simulations or domain randomization. So for example, if you build the same robot twice, then these robots actually have a different behavior, because the screws on one might not be as tight as on the other. And also actuators actually, there is wear over time. So the actuator behavior or the robot's behavior actually changes over time. So by randomizing these simulation parameters, you can actually account for these variations. So for example, mass properties are extremely hard to also estimate accurately. For example, you have electrical boards and components usually don't know the mass properties so well. Mass is sort of easy. You can put it on a scale, right, the component, and measure the weight. But center of mass and moment of inertia, that's less trivial. So we randomize simulation parameters, also for actuators, by the way, frictional parameters and so on. We randomize them, also the frictional coefficients of the ground. So you can walk on many surfaces stably. And so as long as your physical system is within the distribution that you used during training periods ago, you can have a zero-shot transfer onto the robot. First, it just starts to walk. So that's how these skills and bots. So these two items are important. Then we also have to innovate on the simulation side. So for Olaf, the two legs, that's actually an interesting design, by the way. So it's the same leg twice. So we just rotate one of them and mount it basically. We rotate it 180 degrees and mount it. So that's how we can maximize the motion within the workspace. For the two legs, it's sort of actuators are the joints. They're easy to handle with current simulation. Or simulators, GPS simulators. But for the arms, we use so-called spherical linkages. They're actually incredibly interesting because you can hide actuators where there's space in the body. And we also use linkages for the mouth and the eyebrows and the eyes. So usually, GPS-oriented simulators are not good with simulating these closed-loop systems. So not good in simulating these more generic mechanical assemblies or mechanisms. So usually you assume that actuators are joints, and there's a little departure in the designs that we see on the market at the moment. So we built a simulator called Camino, where we brought our expertise from the audio and electronics into the simulations, GPS-accelerated simulations. So we combine basically the best out of two worlds. So we know pretty well how to simulate very complex humanoids, for example, like this Iron Man figure, that has more than 150 moving components without the fingers and without the head. So it's a very significant number of moving components. It's truly a generic mechanism. So we can simulate complexity like that, but at the same time, we can support 3D walking systems, so contact and GPS acceleration. So the name Camino is motivated by the Star Wars universe. So we use Camino because the inhabitants of this planet in the Star Wars universe, they're experts in cloning, and because we clone robots, many robots in simulation, that we thought it was actually an excellent name. So Camino, the ambition there is applying reinforcement learning to any mechanism. So liberate our mechanical engineers to do really smart designs, place actuators where there's space, and remote actuate with linkages. You can use mechanical advantage. So, right now, controls is usually limiting what mechanical engineers can do on the design side. So, with Camino, we hope that we can change that. Camino is actually open source. It's available. It's part of the Newton framework that we co-developed with NVIDIA and DeepMind together. I really encourage you to take a look at that simulation framework. You can build your own GPS-accelerated simulators also. But they have, a few fantastic simulators. So our contribution is basically the Camino simulator from the design research side. So here's the landing page if you want to take a look. Take a photo. Again, it's early stages. Time complexity is still a challenge, but it can actually simulate these more generic mechanical systems. Okay. So the last thing that I want to talk about is bridging the embodiment. Okay. So, the reason why we built humanoids is that we have internet scale data of human motion. Humans basically doing tasks. So we have internet scale data. For the robots that we built, we don't have internet scale data. And usually have a few artist provided motions. So how can we use internet scale data for our robots and build basically foundation models for the future? And so we have a solution for that. It's basically a bi-level reinforcement learning where you train policies in an inner loop and have an optimization on top of that does a really good job in retargeting. So you can see that we can take human motion and transfer or retarget that onto many embodiments, including a quadruped here. Right? So you can get internet scale data onto these robots. So the user input is actually very simple. You just have to define sparse correspondences, so not everybody on one embodiment has to have a corresponding body on the other one. And it's very easy to specify these correspondences. And again, you can then transfer human motion onto, a quadruped, for example. So a very different embodiment. And so in the policy training, we take care of everything, like foot contact, foot sliding. We avoid collisions. Collisions are non-differentiable. That's why reinforcement learning makes sense. So I think it's an incredibly useful tool to bring more data onto these embodiments. So this is the fabulous team that I get to work with every day. We have in a very small team all the disciplines. We build our own robots, build the control stack, all these learning-based tools, even autonomy solutions that I don't get to talk about today. But we also have a global support team that deals with the deployments of these robots. The BDX fluids have been to every park globally, also on a cruise ship, the Bächer. Our Olaf robot had appearances at Disneyland Paris and Hong Kong. So fabulous to have such a support team and such a good group together. So these are the 4 references if you wanted to read up on the material I presented today. And so, just a teaser of what's next.